Good morning, students. Myself, Vijay Shankar from Electronics and Communication Engineering Department, Chevrolet Engineering College. So today we are going to start a new unit, the third unit for the EEE students as per the R16, and fourth unit, second part for the secondary EC students as per R19 syllabus, my dear students, that is sampling. Sampling is a very, very important topic, and it is a small topic, 2 or 3 topics only we have in this unit. Okay, but the derivation part is very difficult. So please listen carefully, my dear students. Otherwise, the derivation part, the sampling theorem, the mostly, so they're asking some questions. What is sampling, as in the part A, and in the sampling theorem proof, if they ask in the part B. These are only the 2 questions we are getting from this unit, and those 2 are also very important. So be alert. Please listen carefully, my dear students. Now, first of all, you can see, before going to the sampling, a brief description about the communication related with the sampling. See, the first operation in digital communication is the sampling. The first operation in digital communication. The first operation in the digital communication is the sampling. You see here, almost all the natural signals exist in analog form. For example, voice, any moving scene, environmental data, etc. exist in analog or continuous form. Such information can be transmitted from one place to another by continuous modulation of the suitable carrier. Carrier means it is having the high frequency. It carries the message signal. Whatever we are saying, it is a voice, and the data is carried by the carrier signal. That is nothing but the message signal, my dear students. Message signal is compared to the carrier is a low frequency signal. Okay. Then this type of communication is called analog communication. This type of communication is called analog communication. In digital communication, the data to be transmitted is sampled at regular intervals. This is a very important matter, students. Whenever you are converting the analog data to the digital data, you have to sample at regular intervals. The digital communication, in digital communication, the data can be transmitted. The data can be transmitted is sampled at regular intervals. Is sampled at the regular intervals. Such samples are then transmitted directly through the modulation of some carrier. Again, here also it is a carrier is there to carry the message signal from one place to the another place. Because the message signal is very less signal compared to the frequency with the carrier. Carries the signal and it transmitted to a long distances. Okay. The first most in the digital communication is nothing but a sampling. So daily we are seeing that it is a natural signals exist in the analog form. Those are voice, moving scene, environment data, and all it is in the continuous form from one place to another place by continuous modulation. It transmitted by the continuous modulation of a suitable carrier, and this type of communication is called analog communication. Coming to the digital communication, the first of all, the data to be transmitted, the data to be transmitted is sampled at regular intervals. The data to be transmitted is sampled at regular intervals. Such samples are then transmitted directly or through the modulation of some carrier. There are various sampling techniques. There is various sampling techniques are there to convert the analog data to the digital data before go transmit the data. The sampling techniques affect the spectral content of the signal. There is a different types of techniques, and that sampling techniques affect the spectral content of the signal. Okay, my dear student. A brief description about the analog communication and the digital communication. How the analog communication is converted into the digital. The first of all, the main in between of these two, we have a sample or the sampling at regular intervals is sampled at the regular intervals, the data. Okay, analog data converted into the digital data. Following by the students. Okay, you see the block diagram of the sampling is analog signal. So the block diagram, analog, signal is analog signal, my dear students, analog, and the another block we have here is sampler, then we'll get here a discrete signal. After sampling a discrete signal only we are getting, my dear students, a discrete. Continuous analog means nothing but is a continuous, discrete, and this discrete signal by using the quantizer, converting into the digital signal. Okay, is a discrete signal after the sampling. It is also we calling it as a digital only, but the time is digital, but amplitude is a continuous, my dear students. Digital means both the time and the amplitude is a discrete, and continuous means the time and amplitude is also the continuous. Okay, and this data is encoded, digital data encoder. Finally, we'll get the digital signal. In terms of zeros and ones. So this is a block diagram of the sampling. The signal is continuous here, continuous signal, and after the sample, this is a continuous signal is sampled at regular intervals. So 0t, 2t, 3t, and 4t, and this signal is discrete signal. Only the time is discrete and amplitude is continuous. After quantization, the signal is a digital signal, my dear students. Digital signal. Okay, and finally, after the encoding, the digital data, whatever it is, having the digital signal output in terms of the zeros and the ones. This is a block diagram of analog signal is converted into the digital signal. The first most here it is a sampler. The first operation in the digital communication is a sampling. Following, my dear students, a brief description. Now the sampling theorem is a very, very important, my dear students. Sampling theorem. The sampling of the signals is a fundamental operation in digital communication. sampling of the signals is the fundamental operation in digital communication. A continuous time signal is first converted to discrete time signal by sampling process. So now only I am explaining with the block diagram. The continuous time signal, the first converted to the discrete time signal by using the sampling process. See here, by using the sampling process. The sufficient number of samples of the signal should be taken so that the original signal is represented in its samples completely. Again, I am saying here, see, the sufficient number of samples of the signal. Suppose the continuous time signal is like this. You can take the samples, divide this continuous time signal into the samples with regular intervals, 0, t, 2t, and so on, my dear students. Okay, the sufficient number of samples of the signal should be taken so that the original signal is represented in its samples completely. If suppose the original signal is the end here, and the original signal is also like this, you have to divide this into the samples. Okay, my dear students, until up to the last one. The sufficient number of samples of the signal should be taken so that the original signal is represented in its samples completely. Also, it should be possible to recover or reconstruct the signal completely from its samples. Okay, by using these samples only, you can again recover this signal, means nothing but the continuous time signal. Okay. Also, it should be possible to recover or reconstruct the signal completely from its samples. From its samples means merge the impulse signals and the given signal x of t. Then after we can, nothing but it is a modulation. Simply saying that modulation, the carrier frequency, the carrier signal and the message signal, it is a modulated. At the receiver end, it is a demodulated. The message signal is separated and the carrier signal is separated. Okay, and here also I'm saying it is example, my dear students, and it should be the possible to recover the or reconstruct the signal completely from its samples. Okay, the number of samples to be taken depends on the maximum signal frequency present, and that samples also, the number of samples to be taken depends on the maximum signal frequency present. Okay, the sampling theorem gives the complete idea about the sampling of the signals. The sampling theorem gives the complete idea about the sampling of the signals. Different types of samples are also taken, that is flat top samples, regular samples, instantaneous samples, etc. So we already say that here there is a various sampling techniques are there. Okay, and these, the different types of samples are also taken here, the flat type samples, regular samples, instantaneous samples, etc. Okay, let us first discuss about the sampling theorem. Then we go for the different types of sampling process. Okay, first you can learn the sampling theorem, then you go for the sampling process. Once again, I am saying what is the sampling. The sampling of a signal is a fundamental operation in the digital communication. A continuous time signal is first converted to a discrete time signal by the sampling process. The sufficient number of samples of the signal should be taken so that the original signal is represented in its samples completely. Also, it should be possible to recover or reconstruct the signal completely from its samples. The number of samples to be taken depends on the maximum signal frequency present. The next point is sampling theorem gives the complete idea about the sampling of the signals. Different types of samples are taken, that is flat top samples, so regular samples, instantaneous samples, etc. Now we go for the first one, the sampling theorem for low pass signals. Sampling theorem for low pass signals. Low pass, we know, my dear students, it allows only the low frequency. Suppose this is a ideal condition, but the practical condition, the low pass characteristics is like this. So monotonically decreases at the cutoff frequency minus 3 dB cutoff frequency. Every time we are taking the minus 3 dB cutoff frequency, my dear students, in the peak value. Okay. The sampling theorem for the low pass signals in time domain. The band limited signal of finite energy which has no frequency components higher than omega hertz. The band limited signal of finite energy which has no frequency components higher than the omega hertz. The low pass filter allows only the low frequency, does not allow the high frequency higher than the omega hertz. Is completely described by specifying the values of the signal at instants of time separated by the 1/2 omega seconds. Okay, or you can see it is a double hertz. The second point saying that the band limited signal is the band limited signal of finite energy which has no frequency components of higher than the omega hertz may be completely recovered from the knowledge of its samples taken at the rate of 2 omega samples per second. Okay, to construct the time separated by the 1/2 omega seconds and to recover the signal, you see here, recovered from the knowledge of its samples at the rate of 2 omega samples per second. For the construction of the signal, it is a 1/2 omega seconds. Following my students, is very, very important. The construction and the reconstruction are recover or see, it is all should be possible to recover or reconstruct the signal completely from its samples. First of all, we are constructing the signal, then reconstruct or recover from the knowledge of its samples taken at the rate of 2 omega samples per second. There is so many points are there included here, my dear students, from the here it's to this one. The above statement of the sampling theorem stated in two parts can be combined. The first part represents the representation of the signal in its samples and a minimum sampling rate required to represent a continuous time signal into its samples. The second part of the theorem represents a reconstruction of the signal from its samples. The first part is represents the representation of the signal in its samples and the minimum sampling rate required to represent a continuous time signal into its samples. The second part of the theorem represents reconstruction of the original signal. And suppose if I am taking this original signal and using these samples, we can merge these two signals, then removing the samples and reconstruct again the original signal. Reconstruction, that is the second part. The second part of the theorem represents reconstruction of the original signal from its samples. It gives a sampling rate required for satisfactory reconstruction of the signal from its sample. The theorem can be combined and alternately stated as follows. Here. A continuous time signal, this is a statement, my dear students. The sampling theorem statement. If any ask in the examination, what is sampling? What is sampling or define the sampling means you have to write this statement. A continuous time signal can be completely represented in its samples and recovered. Here it is, or is there, my dear students? Recovered back if the sampling frequency Fs, F suffix x, my dear students. S means sampling frequency is greater than or equal to 2 omega. Okay, is recovered back by the sampling frequency Fs is greater than or equal to 2 omega. Here Fs is a sampling frequency and omega is a maximum frequency present in the signal. We already seen that. You see here how it gets the number of samples to be taken depends on the maximum signal frequency present here. How many number of samples you can take, that is, it depends upon the maximum signal frequency. Understood, my dear students? That is here the omega. A continuous time signal can be completely represented in its samples and recovered back if the sampling frequency Fs is greater than or equal to 2 omega. Here Fs is a sampling frequency and omega is the maximum frequency present in the signal. Maximum frequency in the signal. Or otherwise, Fs is equal to, Fs is greater than or equal to 2 Fm. Fm. Here it is a omega, it is represented as Fm. Message frequency. Sampling frequency here. Another way we can write the same sampling theorem, a signal which is band limited to, a signal which is band limited to FM hertz, band limited to the FM hertz can be completely recovered from its samples. A signal which is band limited to FM hertz can be completely recovered from its samples if the samples are taken at the rate of Fs is greater than or equal to 2 Fm or Ts, the inversely proportional to the frequency, is greater than or equal to 1 by 2 Fm. Both are the correct. Okay, you can write the definition like this: the continuous time signal completely represented in its samples and recovered back if the sampling frequency Fs is greater than or equal to 2 omega. Here Fs is a sampling frequency and omega is a maximum frequency present in the signal. Okay, here it is a maximum frequency Fm. W is equal to Fm. Not the message here, my dear students. It is a maximum frequency. The signal, the another way, the definition of the sample is the signal which is band limited, If you want to note down the definition, my dear students. If you want a signal which is band limited to FM hertz, the maximum frequency, can be completely can be completely recovered from its samples if the samples are taken at a rate of Fs is greater than or equal to 2 Fm. Okay, this is another way you can define the sampling. Either a continuous time signal and this one, or otherwise you can write like this also. A signal which is band limited to a maximum frequency FM hertz can be completely recovered from its samples if the samples are taken at the rate of Fs is greater than or equal to 2 FM. So very important formula also, my dear students, in the sampling total unit in the sampling theorem also. Okay, if you want to note down this definition also, my dear students, then see, we already know the trigonometric Fourier series formula from the Fourier series. The Fourier transformation definitions is also known. In the Fourier series, mostly we are taking only the trigonometric Fourier series and the exponential Fourier series. Most of times we are not using the compact trigonometric Fourier series. All the properties are derived by using exponential Fourier series only, using either the analysis equation or the synthesis equation. And the Fourier transformation also, all the properties is derived by using Fourier transformation definition or inverse Fourier transformation definition. Okay, now in the sampling theorem, we are using this two Fourier transformation and the Fourier series. The properties of Fourier series and the properties of the Fourier transformation, if possible, and the trigonometric Fourier series and exponential Fourier series and the Fourier transformation definitions to prove the sampling theorem. Okay, completed, my dear students. Already, I hope everybody noticed another definition of the sampling also. The signal which is band limited to the maximum frequency FM hertz can be completely recovered from its samples if the samples are taken at a rate of Fs is greater than or equal to 2 FM. Okay. Now let us go for the sampling theorem proof. The statement to the saying this one, the proof of the sampling theorem. Okay. Let x of t be the continuous time signal shown. See here is a figure. The x of t is a continuous time signal. We already know what is a continuous time signal. Both amplitude and the time. The time is in the x-axis, my dear students, here, and the amplitude is in the y-axis, x of t signal. Both are continuous. You can call it as a continuous time signal. Okay. In the figure A here. The figure B, all the samples, and figure C is combining of the signal, original signal and the samples. We are saying this signal is a discrete time signal. Let the signal be of finite energy and infinite duration. Finite energy and the infinite duration means minus infinite to the infinite. And suppose that x of t is strictly band limited. Strictly band limited. So the signal which is band limited to the maximum frequency FM hertz. So suppose x of t is strictly band limited. That is, x of t does not contain any frequency components higher than omega hertz. Higher than omega hertz. A sampling function samples the signal regularly at the time rate at a rate of fs samples per second. Fs samples per second. See, these are the regularly at a rate of fs samples, nothing but the sampling frequency. Sampling frequency fs is units or samples per second. How we got these values of the delta of t minus n into ts? Let if I am taking the delta of t here, what is the delta of t saying that at t is equal to 0, the magnitude is a 1. T is equal to 0, the magnitude is a 1. Now the second I am taking here delta of t minus ts. And shifting towards the right side with the ts samples. This magnitude is also 1, my dear students. Okay. And the second one, delta of t minus 2s, 2ts, or the 2s, 2ts, shifted towards the two samples, the same amplitude 1. And then towards the left side also, if it is a shifted delta of t plus ts, one sample to the left side, minus ts, and another sample if I am taking here, delta of t plus 2s. The two samples is shifted left side, minus 2ts is a minus ts. All the amplitude is the same, 1 on. Now combine all the functions here. All the functions, my dear students. So now I am combining the functions. First one is delta of t plus ts. Delta of t minus ts. I'm adding these two functions. So this value also will get the 1. Plus delta of t minus 2ts. It is also added 2ts. 1. Because here you can add these two. Here 1 plus 0 is a 1. And here the 0 plus 1, 1. And if these two are added, again this delta of t minus ts, z1 plus 0 plus 0, here 1, 0 plus 1 plus 1 is a 1, and 0 plus 0 plus 1, again it is a 1. And so on towards this one. And it is also added on the left hand side, the t plus ts minus ts plus delta of t plus 2ts, advanced signal, minus 2ts. So on from minus infinite to, and here the so on infinite. Okay, my dear students. See, having the infinite duration, the signal to be fired. This signal is a finite energy and infinite duration. That is the original signal x of t. And the samples also, you can take the duration is a infinite duration. Now, after adding all the impulse signals, shifted impulse signals, what we'll get here it is a 0, 1 into ts, 2 into ts, and so on. If I write this as a sum of n is equal to minus infinite to infinite delta of t minus n into ts. Okay, my dear students, sum of the functions, all I'm adding these functions, it takes a minus infinite, so minus n value is minus infinite and so on. And let us see here the minus 2. Minus 2 means t plus 2ts is the first one. And minus 1 if it is n is equal to t plus ts. When n is equal to 0, delta t. When n is equal to 1, delta of t minus ts. N is equal to 2, delta of t minus 2ts. Okay. All the impulse signals added from the duration of minus infinite to infinite, you can write as a sum of n is equal to minus infinite to infinite delta of t minus n into ts. Got it, my dear students? The sample, the original signal x of t. Now I'm taking the delta of t minus n into ts is the sum of all the functions. Okay. Then these two signals, okay, combined, we can call it as x delta of t is equal to x of t into the sum of n is equal to minus infinite to infinite delta of t minus n into ts. So now I'm combining the functions. So modulation, nothing but is a product. We already seen time modulation or the modulation in time. Okay, my dear students. So now product of these two functions, call it as x delta of t. X delta of t. See here, the given x delta of t. Combining all the functions at minus ts, minus 2ts, minus 3ts, minus 4ts, and so on. Because it is going decreases in the negative, the samples also, wherever it is, ants combine the function. Okay, the figure A shows that continuous time signal and B is unit impulse train used as a sampling function. And C is a sampled version of the signal. The sampled version of the signal in A is a continuous time signal. After the samples, the sampled version of the signal in A here is after the, is called it as a continuous time signal, and this signal we are calling it as a now the discrete time signal, because amplitude is a continuous but the time is discrete. But here the time is continuous and the amplitude is also continuous, my dear students. Following is a very important, the definition, the statement, and how we are taking, how we are combining, how we are taking the samples, the sum of n is equal to minus infinite to infinite delta of t minus n into ts. Okay. Then the sampling frequency, the ts and the inversely proportional to relation is there here for the time and the frequency. So the impulse, the time space between of any two successive samples is t seconds. The time space between any two successive samples is t seconds, shows the impulse train of the frequency, impulse train of the frequency equal to the sampling frequency fs. The figure C shows the instantaneously sampled version of the signal x of t. Following my students, the impulse train of pulses can be expressed as, you see here, I already told the sum of n is equal to minus infinite to infinite delta of t minus n into ts. Let x n into ts represents the instantaneous amplitude of the signal x of t at instance t is equal to ts. Now the signal after the sampling, the x of t becomes, it is now the x of n into ts. X of n into ts. The amplitude is shown by encircled dots in the figure A. Each impulse has amplitude equal to 1. Therefore, we can say that the waveform shown in the C is obtained by multiplying the unit impulse with instantaneous values of the x of t. Multiplying the instantaneous values, that is x of n into ts. X of n into ts, my dear students. Why I am taking it as x of t, now it becomes of x of n into ts. It is multiplied with the delta of t minus n into ts. This varies. Okay. So x delta of t is equal to, after sampling the original signal, x delta of t is equal to sum of n is equal to minus infinite to infinite delta of t minus n into ts x of n into ts. Okay, my dear students. How we can write this function? See the x of t. I already told that some properties of the impulse function. X of t delta of t is equal to, again we have x of t minus t naught. Let us take it as of t minus t naught, my dear students. Then you can understand x of t delta of t minus t naught is equal to, is x of t naught into a delta of t minus t naught. Means at x of t will get only at the t naught is equal. Otherwise, x of t into delta of t is equal to, delta of t is 1 at the t is equal to 0. So x of 0 into delta of t at one value on. If suppose the signal x of t delta of t minus t naught, now it is again, it is let us the beta. What happens at the beta, the x of beta into delta of t minus beta. Means suppose there is a different signals are there in the x of t. It is multiplied with the delta t function at t is equal to 0. If there is any value, the remaining all the values is a 0. Only will get at the t is equal to 0 only. So the x of t is equal to 0 means x of 0. You see here x of 0 and delta of t. Suppose the x of t minus t into delta of t minus t naught, the shifted version. There is no any value in the 0 here, only at the t naught only. Now this value is multiplied with the x of t, the remaining all the values is zeros. So at the t naught is equal to, at t naught is equal to of the signal x of t is multiplied with the delta of t minus t naught. Follow my difference. These are properties of the delta function. Okay. You can also write like that as a x of t delta of t is equal to x of 0 into delta of t. X of t delta of t minus t naught is equal to x of t naught into delta of t minus t naught. Now we got the one idea how we got this expression x delta of t is equal to sum of n is equal to minus infinite to infinite delta of t minus n into ts x of n into ts x of n into ts. Now only I explained x of n into ts. Understood? Thus x delta of t is represented by multiplying equations by x of n into ts. Since the width of the impulse in delta of t approaches at the zero, it represents only the instantaneous value. Therefore, this method is called instantaneous sampling. It is also called ideal sampling. It's also called ideal sampling. Now, then, here delta of t represents the sampled version of continuous time signal x of t, the Fourier transform of the impulse train. Now, on applying the Fourier transformation on both sides. Fourier transformation on both sides. What is the x of t Fourier transformation in the frequency? X of omega or x of 2 pi f in terms of the normal frequency. Okay, my dear friends. And it becomes of fs sum of n is equal to minus infinite delta of f minus n into ts. The t becomes of f here and the ts is becomes of fs, and the x of n into ts is a fs, where here the fs is a 1 by ts. How we got this function? These are very important, my dear students. Okay. Everybody got idea how we got this equation, but after applying the Fourier transformation, on both sides of this signal, left hand side we can understood the x of t nothing but the converting of time domain to the frequency domain is x of f only. But here the sum of n is equal to minus infinite, the delta function is in turn converted into the frequency. But how the x of n into ts is becomes of fs? How the x of n into ts is becomes of fs values after applying the Fourier transformation for the impulse train. Therefore, the Fourier transformation of the wave can be written form as x delta of f is equal to again you can see here fs is sum of n is equal to minus infinite the delta. Now it is writing that x of f minus n into fs. There is a little bit confusion, my dear students, of these two equations. How we got these two equations? To get these two equations, we have to go for the trigonometric Fourier series equation, my dear students. Trigonometric Fourier series. Before applying the Fourier transformation of the signal x delta of t is equal to sum of n is equal to minus infinite delta of t minus n into ts x of n into ts, have to see the delta of t as a Fourier series function. Okay, my dear students, as a Fourier series function. Trigonometric Fourier series. What is a trigonometric Fourier series? There is a three functions. One is a0, second one is an, and the third one is a bn. Okay, my dear students. Three terms as of the trigonometric Fourier series. So what is the formula for the trigonometric Fourier series of a naught is equal to 1 by t and an is equal to 2 by t, the integral of, and bn is equal to 2 by t, the integral of t, the x of t, and here also the x of t and something when we are taking the x of t signal. An is a cosine function and the bn is multiplied with the sine function. Adding of all the three terms are nothing but coefficients. These are a naught and an, and the bn is the coefficients. In the trigonometric Fourier series, x of t is equal to a0 plus an into cos function plus bn into sine function. These are the coefficients one. How we can find the coefficients means a naught is equal to 1 by t into integral of something, and an is equal to 2 by t, the integral of x of t into cosine function. Bn is equal to 2 by t into x of t sine function. We know all these functions in the Fourier series of the trigonometric Fourier series. Let I am taking it as delta ts of t, nothing but the delta of t at the sampling frequency. The impulse signal at sampling frequency A naught plus, because I am taking it is after the sampling, it is a discrete only, my dear student. Discrete means integral, we are not using the integral, sum of only. Whenever it is a digital and the discrete signals, always you can use the sum, convolution sum and convolution integral. Convolution integral is applied for the continuous time signals, convolution sum for the discrete time signals. So I'm taking here the samples, frequency samples or the TS of delta T. The n is equal to 1 to infinite. Why it is a 1 to infinite? Here it is a A0 is already got it for n is equal to 0. An into cos n omega s into t. Because n is equal to 0, the cos 0 is a 1 and a naught. And sum of n is equal to 1 to infinite. So for the sine function 0, Bn sine n omega s into t. See, all it is a sample frequencies only. There's an equation of the trigonometric Fourier series for the delta. If I am taking the delta of t instead of x of t, delta of t ts is equal to a naught plus sum of n is equal to 1 to infinite an cos n omega naught s into t plus sum of n is equal to 1 to infinite bn sine n omega s into t, where a naught is equal to 1 by ts integral ts, because it is a sampled time, delta of delta ts suffix, my dear students, it is delta of t dt, and an is equal to 2 by ts. See, for any confusion, all it is a 2 by ts here, and now here I'm writing the a naught by 2. Okay, so actually the a naught is a 1 by ts. Now I'm writing here the a naught by 2 and write it is a 2s. Nothing is confusion, all it is a 2 by s only. Integral ts delta ts of t. Actually here it is x of t. That x of t I am taking the delta of ts into t, my dear students. Cos n omega s into t dt, and bn is equal to 2 by ts integral ts delta ts of t, instead of cos here for n, and now here it is a sine n omega s into t dt. These are the coefficients in the trigonometric Fourier series function delta of t ts. Okay, my dear students. Following. Now, if I am taking the delta of ts, what is the impulse train function? Delta ts of t is a 0. The value is 1 at t is equal to 0, and at t is equal to ts, the value is 1, but what is the function here? Delta of t minus ts, and this function is a delta of t. Okay, and 2ts, this value is magnitude is 1, but it is a delta of t minus 2ts, and so on. And coming to the left hand side, the ts minus ts, The magnitude is a 1. What is the delta function here? The t plus ts. In this delta, ts of t is equal to only the sum of all the terms. When n is equal to 1, t minus ts. When n is equal to 0, delta of t. When n is equal to 2, delta of t minus 2ts. When n is equal to minus 1, t plus 1 into ts. Okay. Then minus 2ts. What is the delta function here? The delta of t plus 2ts. Combining all the terms, you'll get the delta t of s. In the trigonometric function, I am taking the x of t as a delta of t here. It is equivalent to a naught by 2. And a naught here takes as t by ts minus 2. Okay. Now, if I am taking the a naught to find, the a naught is equal to 2 by ts integral. It is in between of minus ts by 2 to ts by 2. Let us say if I am taking. So ts by 2 minus ts by 2 is here. And plus ts by 2 is here. In between the range if I am taking. Delta ts, delta t of t, delta ts of t dt is equal to. What is the value here? The minus 0 here. Only one value will get 2 by ts at minus ts by 2 the ts by 2. The value is only at t is equal to 0. So 1 at t is equal to 0. Okay. Delta of t is equal to 2 by ts. A naught is equal to, we got 2 by ts. Keep it that one. A naught is equal to 2 by ts. Then an is equal to. How you can find an? An is equal to, what is the formula? 2 by ts. Again, if I am taking that as a minus t by the t by 2 or minus ts by the 2 minus ts by 2 delta ts of t cos n omega s into t dt. Okay, my dear folks, my dear students. See the delta of t. Delta of t is a 1. Delta of t is equal to 1 in between of the minus t by the t by 2. And here the value is, what is the value? Cos n omega naught into s. Any function is multiplied with the delta. Again, we'll get at 0 value only. I already said that x of t, delta of t is x of 0, delta of t. Means at the 0, the value is 1 here. Whatever the value you'll get at the t is equal to 0, the x value, you can write it here 1 into something, you'll get x of t on. X of t or x of 0. The value at x of 0, x t is equal to 0, the thing what x of 0. So here the n is equal to 0, the cos 0 is a 1 and delta of t is a 1. Again for these also, you'll get the 2 by ts only. 2 by ts. So an is equal to 2 by ts. And now Bn is equal to 2 by ts integral minus ts by 2 the ts by 2 ts by 2 delta ts of t sine n omega s into t dt. See now here also at t is equal to 0 only the value is 1. So delta of t at t is equal to 0 is a 1, and sine n is a 0, means sine 0 is a 0. So Bn is equal to 0, we got. Bn is equal to 0. Following my students. So now we can substitute these coefficients. A0 is equal to 2 by Ts, An is equal to 2 by Ts, and the Bn is equal to 0. There is no, the last term for the delta of T is equal to A0. What is A0? 2 by Ts. 2 get cancelled, 1 by Ts. Sum of n is equal to 1 to infinite An 2 by Ts cos n omega s into T. Okay, now it changes as by using these equations, 2 get cancelled, 1 by A0. A0 means 2, Ts. T is also cancelled here. Ts. An is equal to 2 by Ts. 2 by Ts. That becomes the Bn is equal to 0. So delta Ts of T is equal to Ts plus sum of n is equal to 1 to infinite 2 by Ts cos n omega naught s omega s into T. Following my dear students. Now to get x delta of T, x delta of T is equal to x of T multiplied with the x Ts of T, the sampled version. So what is the x of T? X of T can take the original signal. Now we got the x delta T of S is a Ts okay, A0 is a 2 by Ts, my dear students. It is not the Ts, 1 by Ts. 2 to get cancelled, it will get the 1 by Ts, not the Ts. 1 by Ts plus sum of n is equal to 1 to infinite An. An is a 2 by Ts cos n omega s into T is equal to x delta of T. X delta of T is equal to x of T. Delta T s of T, by using the trigonometric function, we got 1 by Ts as A0 plus sum of n is equal to 1 to infinite the 2 by Ts cos n omega s into T. Now you can expand this function with x of T. Then x delta of T is equal to x of T by Ts plus x of T by Ts, here see, 2 into cos, I'm taking the n is equal to 1 now, cos n is a 1 omega st plus expanding this one, x of T by Ts 2 cos 2 omega s into T plus so on. What is the next one again? X of T into 2 by Ts cos 3 omega s into T and so on. So now we can apply the Fourier transformation. Now we can apply the Fourier transformation in the left hand side. It becomes of x delta of f is equal to, what is the x of T Fourier transformation is x of omega. So in terms of the normal frequency, x of f into Ts plus x of T by Ts into 2 cos omega s into T means it is a Fourier transformation of the signal x of T with the cosine function. Cosine function means let us take the x of T cos omega s into T. The Fourier transformation is this cos omega T. Cos omega T, we can write it as exponential function. Exponential function 1 by 2 e power minus j omega T. plus 1 by 2 e power minus j omega t. Okay, from that the 1 by 2 into x of f minus fs plus x of f plus fs. Okay, my dear students. These are x of t cos omega s into t Fourier transformation. So x of t by the ts is there. Then we'll get 1 by ts. If the 2 is already there, the Fourier transformation is a 2. 2 to get cancelled. X of f minus fs plus x of f plus fs. For the second one, 2 omega s is there. So for the next value, the 1 by ts, x of f minus 2fs plus x of f plus 2fs and so on. Then it becomes of x delta of f is equal to, take the f, 1 by ts is a common, sum of n is equal to minus infinite to infinite. We can write as n is equal to 0 is x of f minus n into ts. So here the plus values is there, minus values is also there. So x delta of f is equal to 1 by ts, n is equal to minus infinite to infinite, x of f minus n into ts. See here, this is the function. X delta of f is equal to fs. What is fs? Nothing but 1 by ts one. Sum of n is equal to minus infinite to infinite, x of f minus n into fs. Minus n into fs. Actually, it is a 1 by s actually. 1 by t you have to get, because in terms of the t, 1 by ts, omega s is nothing but that we can get, it is a numerator. F into n into fs. Okay, my dear students. Here the omega is there. Omega means 2 pi fs. So f minus fs and f plus fs. Okay, now we got the idea. Before applying the Fourier transformation, using the trigonometric Fourier series, I have to derive the equation of x delta ts of t, combining with x of t, the original signal. Finally, after applying this equation as a Fourier transformation, we'll get x delta of f is equal to fs, sum of n is equal to minus infinite to infinite, x of f minus n into fs. Following my students, it's a very, very important. Up to this is a sampling theorem, the statement and the theorem. The remaining part is there, is only the construction, and then the recovery is there. Following my students, in the tomorrow class we continue the second part, how we can recover by using the fs is greater than or equal to 2fm. fm is a maximum frequency and fs is a sampling frequency. How we can recover the original signal from the sampling frequencies or the maximum frequency. Got it, my dear friends? Once again, in the tomorrow class, I will again you can explain this total proof by using the trigonometric Fourier series, and then you can apply the Fourier transformation. How we get this x delta of f is equal to fs, sum of n is equal to minus infinite to infinite, x of f minus n into fs. I will explain the whiteboard, my dear students, the tomorrow class also. Don't worry for that one who are not understood today's class. The tomorrow class I will again explain this, then you go for the next topic. Okay, the continuation, not the next topic, the continuation part. Okay, there's so many things is there here to get it is a final derivation part. Okay, any questions? Okay, thank you.